Alright, section 2.7, solving equations in one variable. This is going to be a pretty short section and pretty easy. We're just going to solve some equations that have fractions in them, and the first step on this is going to be to multiply by a least common denominator to get rid of our fractions. The problem is that because of there being x's in the denominator that we're getting rid of, we can end up with some what's called extraneous solutions, which means when you solve it, you get it as a solution, but it's not actually a solution. So it's going to be really important on all of these for us to go ahead and check that the solutions really do work in the original equation. So let's look at this first example. X plus 5 equals 14 over x, and my common denominator for this would be x because that's the only denominator I have. So I'm going to take this and multiply the whole thing by an x and distribute it through my equation. Okay, well, x times x gives me x squared. X times 5 gives me 5x. And x times this fraction, the x's will cancel out and I'll just be left with equals 14. Okay, so let's think about how to solve this. I have a quadratic equation. Okay, because it's to the second degree, let's get everything on one side and see if it's possible to factor. Okay, so I'd subtract the 14 over. Let's see, well, 2 times 7 gives us 14, and if I make the 2 negative, then that will give me 5 when I add them together. So let's see, that's plus 7, because I want it to be a positive 5, and minus 2. So that means that x equals negative 7 and positive 2. Okay, now those are two solutions that I got. Let's see if they're both actually solutions. So I'm going to plug back in negative 7 and 2. So negative 7 would be negative 7 plus 5 equals 14 over negative 7. Well, negative 7 plus 5 gives me a negative 2, and 14 over negative 7 gives me a negative 2. So negative 2 does equal negative 2. That looks like that solution is right. Now let's try positive 2. We get 2 plus 5 equals 14 over 2, which means I have 7 equals 7. So that checks out. So both of these really are solutions. X equals negative 7 and x equals positive 2. So that one was pretty easy. They're going to get a little bit more complicated. Let's look at an example like that. Okay, we have x minus 3 over x minus 3 over x plus 1 plus 3 over x squared plus x equals 0. Now, the first thing we need to do is find the least common denominator of this. And so if we have a denominator where we can factor, that's going to be something helpful to look at. Is that denominator, I can factor an x out and get x times x plus 1, which means this fraction, the denominator, is really a combination of these two fractions combined. That's actually a good thing because that means we have to multiply by less. My common denominator is this because it has an x and it has an x plus 1 and it has the x squared plus x that this one has. So we're going to multiply our fraction by x times x plus 1. So for my very first fraction, the x's cancel out and I'm really just multiplying my numerator, x minus 3, by x plus 1. On this one, I have the x plus 1, I need the x, so I'm doing negative 3 times x, which is minus 3x. This one has the whole denominator, which will cancel out, so we just have plus 3, and that equals 0. Okay, so let's go ahead and solve this out. This we would FOIL and get x squared. We get 1x and negative 3x, which gives me negative 2x. Negative 3 times 1 is minus 3. And I still have the rest of this. Now if I add my like terms, the negative 3 and the positive 3 cancel out, and I have x squared minus 5x equals 0. I can factor that and make it x times x minus 5. So that means my solutions are x equals 0 and x equals 5. So all we have to do now is check to see if any of those solutions are extraneous. Alright, so we're going to plug it back into our original equation. If I plug in 0, I get 0 minus 3 over 0. Oh no, I'm dividing by 0. That's impossible. So apparently 0 is not really a solution. Okay, if I plug in 5 minus 3 over 5 minus 3 over 5 plus 1 plus 3 over 5 squared plus 5, that needs to equal 0. Sorry, that over there. So that's 2/5 minus 1/2, because 3 over 6 is 1/2. See, 25, that makes 30. 3 over 30 is 1/10. Common denominator here is 10, so that makes that 4 minus 5 plus 1 all over 10, and so that is, what, 4 plus 1 is 5, minus 5 is 0, so the top of this gives us 0, so 0 equals 0. So x equals 5 is a solution. There's another way that we can check on these to see what our zeros are, and that's by graphing. Okay, so on my calculator, if I plug in what I have originally, then the only complicated thing here is making sure that you get it all in there right. So x minus 3 needs to be in parentheses, divided by x minus 3 divided by the bottom needs to be in parentheses. Anytime I have more than one thing basically on the top or the bottom, it's going to need to be in parentheses. Plus 3 over x squared plus x. The reason we can use the graph for this is because it equals 0. If it didn't equal 0 on the right side, we'd have to move whatever was on the right side over, and then we could still look at it. Okay, so I'm going to take a second to let you look at that without me shaking the camera too much, hopefully. And then I'm going to graph. Okay, so we can check this basically just by looking at it and say, okay, looks to me like obviously 0 was not really a solution. And then if you trace maybe to help you out and you move over, okay, then right here where we're getting close to y equaling 0, it does look like we get close to 5. And we could even calculate that 0 if we wanted to find it out for sure. So you may be asking, well, why can't I just do this all on the calculator? Well, sometimes you can, and sometimes it's not actually going to give you the answer we want. And the issue here is basically if our instructions ask us for an exact value. Let's take a second to talk about exact value. Exact value in mathematics sounds completely backwards than what you would want in the science field. Okay, exact value in mathematics means that I would prefer 4 over 5 over a decimal like 0.8. That I would rather have this than this. This is an exact value. This would not be considered the exact value. Now that's kind of a weird case because really those are saying the same thing. So it really applies more to I would prefer 1/3 over 0.3 repeating. Because can I put 0.3 repeating into a calculator to continue doing calculations with it? No. I can put 1/3 in, okay, and then it will use the actual decimal you get or the interaction you get with this fraction. The calculator will actually use it. The other thing is if I'm using the quadratic formula to solve something and I get something like 2 plus or minus the square root of 11, this is an exact value. the decimals you get from this are not. You have to round when you write down that answer. So this is an exact value. The decimal approximation of that would not be. So that's why it is good to know how to do it algebraically and graphically, because if you do a graph and you end up with a decimal that repeats for your zeros, then you know that you have something irrational like this, and if it asks you for the exact value, you would want to go back and figure out how to get that algebraically, where you would end up using the quadratic formula. Okay, so this is pretty much all there is to 2.7, solving these equations and checking to see if all the solutions you get really are solutions.